the curves with the differentials.
Thank you. So the most important part of this talk is this announcement, of course. So we are organizing with Leon and Babak Madami, who is not here, a school for graduate students in this room. And if you like the place, tell your graduate students to apply. I hear an echo very strongly. I don't know whether that's supposed to be the case. I can move this down. Okay. So this is going to be about compactifying things. And I'll spend a lot of time on motivating the problem. And this is not an audience I know so well. So if I go too fast, ask me questions. Equally importantly, if I go too slow, just snore very loudly and I'll get the hint. Okay. So I want to do some specific, I want to introduce some notation, sorry. And this is an easy enough notation. So omega mgn, so mgn is moduli space of curves of genus G with n distinct marked points. And I'll tell you what this is. So this is x, z1, zn, omega. So x is the Riemann surface, smooth Riemann surface. Z1, Zn are distinct points. And omega is a holomorphic differential on this Riemann surface. Depending on your preferences, you write it this way, or you write it that way, or you write it any other way you choose. But this is the main subject of the conference, so you all know what holomorphic differentials are. Okay? So this is not a particularly interesting space. So this is just a vector bundle of rank G over a moduli space of curves, which is a very classical object. What I'm interested in is some subsets of this, and these are called strata. And please don't interpret the word stratum too strongly. So mu. So this is a set of all this data such that the divisor of zeros of omega, I don't know how you want to write it, divisor of zeros, whatever, is equal to the sum of mi zi, where mu is equal to a tuple m1 through mn, and the sum of mi is, of course, 2g minus 2, because a holomorphic differential has precisely 2g minus 2 zeros. Okay? So this is the locus of smooth curves with n distinct points with a holomorphic differential such that its zeros are precisely at these points and have the multiplicities mi. Okay? This is a stratum because, of course, the union of such overall mu is that space. No, I'm being sloppy because, of course, in general, if I take omega, it doesn't have zeros here. So it's a stratification of a different space, but never mind. This is why they're called strata. And I'll say the word stratum. I won't put any particular meaning, except this is a shorthand way of saying this. Okay? So this is such a space. And you can generalize this. You can say for any k, which is an integer, I can define omega k mgn mu be the space x, z1, zn. This piece of data still is a smooth genus G Riemann surface with n marked points, but omega now is going to be a section of k times the canonical bundle. So this is a k differential. Okay? You can do this for positive k, for negative k. It's only interesting to do it for non-negative for the following reason. Here mu, is again a collection of points m1, mn, but the only difference is that the sum of mi is equal to 2g minus 2 times k. And of course the condition here is that the divisor of zeros of omega is equal to the sum of mi zi. Okay, so this is a generalization. And you can do this. I know that there is one most interesting case, perhaps. So I didn't tell you what mi's were. So mi's, for me, are integers. And I don't really require them to be positive, even though in 2 minutes I'll pretend they are, because for the purposes of this talk, this is good enough. So this could be a meromorphic differential. If I say that's a meromorphic differential, it doesn't sit in that space anymore, so I don't want to worry about that. So you should know that whatever I say works in the generality of meromorphic k differentials, but all I'll do on the blackboard will be holomorphic one forms, and you'll trust me that I can do the general case as well. Okay, but notice that there is parameter k of k differentials, and clearly there is one most interesting case, perhaps, when k is 0, and this is called the double ramification cycle. And you can think of this as the locus of curves x, z1, zn, and I have numbers m1, mn, such that the sum of mi is 0. No. And now I have a function f, because the 0th power of the canonical is trivial, so it just means it's a function f from x to p1, such that if I take the pullback of the divisor infinity minus 0, I get the sum of mi zi, which is a fancy way to say that I want to have a meromorphic function with prescribed preimages of 0 and infinity with prescribed multiplicities. The way I've written this is I wanted to emphasize that this locus, which I will denote dr for double ramification, g and mu, is in a way a close cousin of the locus I'm interested in. I'm not going to handle that. This case is special. Somehow k differentials are not special. This is special because there is not a differential, it's a function. Things are different. If you have k being negative here, just flip the signs of everything, that does nothing. So I'm not missing out by saying that I'm going to consider only positive numbers. So let me tell you what the goal of this talk is. Well, the goal of this talk is to make you attend the graduate school, but the other goal, maybe make your students. I mean, do tell your students to apply. So goal, compactify in a good way. And for the purposes of this talk, I'll only do the stratum of holomorphic differential. So I will be speaking only the case for all mi greater than or equal to 0, and I'm only talking about holomorphic 1 forms. I could be doing meromorphic 4 differentials. Some of the things we know how to do, some of them we don't. But for pedagogical purposes, that's all I do. I won't say so much about the double ramification locus, and we don't have so much. It's a different story. But this is my goal. Okay? And I'll remain vague about what exactly good means for a while. Okay? But before I go into trying to explain to you what it is that we actually try to do, I'd like to try to motivate this goal. And as you can see, my voice is about to go out at some point. So you're not supposed to bring drinks into this room. Okay. Yes?
Over the compactification of MG bar?
So in principle, of course, you can take anything. I know what you're asking. Sorry, I think I know. And you'll tell me otherwise if not. So this is something that sort of clearly maps to MGN, right? Because I can forget whatever data and just I have a curve with a bunch of points. And then when I say compactify, one of the good properties of a compactification would be that the compactification should also map to MGN bar somehow. This is what I'll require. And it's sort of natural to expect this to happen if you want to have a nice compactification. So yes, the compactification I'll construct will admit a forgetful map to MGN bar. Okay. But it will have many other properties. And I won't really construct it, but I'll describe what the properties are. But I want to motivate maybe why this is an interesting question. If you think it's interesting already, very good. But there are some motivations I know. So motivations, if you're doing Teichmuller dynamics, then there is an SL2R action on a stratum, which is defined in the way it is defined. I don't want to go there. This is, for me, only motivation, even though this was one of the large things for us to think about. So I want this. So there was this very interesting dynamical system. And there are hundreds or thousands of papers written about that. So if you have an action of a group in a space, you want to classify all orbits or maybe all orbit closures. And you can prove rather easily that any orbit closure will go to the boundary. That if I have a one-point compactification, if I define a one-point compactification of this space, then every orbit will contain this boundary point. So this means that if I do any other compactification, all orbits will intersect my boundary. So this means you can try to understand orbits by looking at their degenerations. Orbit closures, really, but never mind. Okay, that's one motivation. Another motivation from the point of view of modular of curves, I mean, these are interesting geometric loci in, well, sort of MGN, if I forget. And you can try to use them to learn more about the cohomology or the showering of MGN. And really, you would like to know more about the cohomology of the MGN bar. This is not the direction I'm going to go, but this is these meaning the strata. Well, not really the strata, but you forget some data and you get an object. Okay. These are some motivations. There is one other, perhaps, motivation that I'd like to mention, just maybe to pique your interest, but not really to. I'm not going to say anything of the sort. And this is not a subject that I'm going to dwell in, so I'm going to ignore the double ramification loci after I write one line. So the double ramification loci, cycles, whatever you call them, are needed to construct a suitable symplectic field theory. I mean, there is a bunch of adjectives here. Symplectic field theory. Their closures are needed. And I can try to explain to you why that's the case. So here is a curve that I am thinking of as a map to P1 with prescribed preimages. This is P1, and this is the infinity on P1, and this is 0 on P1. So this is a point in the double ramification locus. And now I have another curve that also has a map to P1. This P1 also has a 0 and infinity. And if I prescribe the behavior to be the same at infinity of this curve and at the 0 of this curve, I can glue them. Okay, and there's some kind of gluing procedure. And this kind of gluing procedure is necessary if you want to do a suitable field theory. And you will see that when I glue, I certainly get a non-smooth Riemann surface. However, I choose to resolve the singularities, it's not going to be smooth. So certainly I will have to go into the boundary. So certainly I will then need to understand what the closure of this locus is. This is only a motivation abstractly because we're not really touching this question. But this is something you can also ask. Okay? I could, but I don't want to write it. So you have your holomorphic one form, call it omega, right? Locally near every point, your form can be written omega as dz. This defines the local holomorphic coordinate at that point up to translating the coordinate. Z is a complex number. A complex number is also known as a point in R2. You can act by SL to R on R2. So Z, you will take the complex coordinate and rotate and stretch it in some way according to your element of SL to R. So you'll get a new coordinate Z prime. And then you say that my new form will be D of Z prime. This is no longer a holomorphic form for the original complex structure because if I stretch the real direction by a factor of 2, this is no longer holomorphic. But now I'll say, and I'll now take a complex structure on the surface, on the same topological surface, for which this new form is holomorphic. You have to worry what happens near zeros, it all works out. That is the action. Okay? But this is all I wanted to say about the action. And you can do this for higher degree. There are issues with poles that I don't want to talk about, but that's all. Okay? Are we sufficiently motivated? Any questions? Okay. So, what kind of compactification could you construct? Well, you can construct all sorts, but you want something nice and geometric and reasonable about it. The way I define my strata, the stratum of holomorphic differentials with prescribed zeros with prescribed multiplicities is a subset, certainly, of this space, right? So let me compactify this space first. So omega mgn over mgn. This is a rank G vector bundle. Right, the fiber over every point are just the holomorphic one forms on that point. I know how to compactify this. We learned this from Deligne and Mumford many years back. This is the Deligne-Mumford compactification by stable curves. I'll remind you what stable curves look like in a few minutes because I want to draw pictures anyway. I'll do some example. Okay, so these are things that are Riemann surfaces but have nodes, and there is some way to keep track of them. So I can compactify that, and it turns out you can compactify the bundle so that this remains a rank G bundle. Okay, complex vector bundle. So what is this? This is nodal curves. So this is an object here looks like X, which is a union of its components, let's call them XV, meeting at a bunch of nodes. Okay? And I have to tell you what the fiber is over this point. So if I have something like that, a fiber will be a collection of omega V, such that omega V is a meromorphic one form on XV. Only singularities are simple poles at the nodes with opposite residues. Okay? This discussion here does not care about the points. So what I really did is I said do this without points and then just throw in the points as irrelevant to the rest of the data. Okay? So let me try to do this in an example so that I can introduce the notation for stable curves, or the pictures for stable curves. So this is a sort of a continuing example that I used to explain what the difficulty is eventually. So I want to look at M2 bar. Okay? So M2 bar contains M2. I know that all the curves are hyperelliptic. We're not going to use that. But also it contains a curve that looks like this. There is one torus and another torus here. Okay? And they meet at a node. So this is a bad picture. They meet transversely. This is hard to draw. So I'll draw what is called a dual graph. So I draw a vertex of a graph for every irreducible component, and I draw an edge for every node. Okay? So this is how I'm going to draw such a point. And on the other hand, I also have an object that looks like this. So this is nodal again, but this is sort of a self node. The component intersects itself. So there is only one vertex, right? Because there is only one irreducible component, and there is one node which corresponds to a loop from that vertex to itself. Okay? I imagine that 95% of the audience have seen these pictures before. This is what I'm doing quickly. Okay? Fine?
The graph doesn't indicate sort of how the genus is distributed.
So you may want to put the genera here. That's a good idea. How about I put the ones? Okay, this indicates the genus of each irreducible component. And here the genera add up to 2. And here there is genus 1, and there is also a loop, which indicates there is an extra 1. Okay, now let's call these components x1 and x2, right? So I want to know what are holomorphic differentials here. So here I'm supposed to have omega 1. Let's call this point Q. Okay, so omega 1 is supposed to be a meromorphic differential on x1, which maybe has a pole at the point Q. But it can only have a simple pole at the point Q. The Resi theorem tells us there is no pole there. So this is the same as this. Okay. And omega 2, by the same token, is also a holomorphic differential on x2. There is a one parameter family of such. There are vector space of holomorphic one forms on the elliptic curve is 1. This is another one. So the total dimension of the vector space is 2. It all works out. Here, I only have one component, and omega is a section, is a meromorphic differential with, well, this point Q has really two preimages on two sides, Q1 and Q2. So it's really and this is not x, this is a normalization of x. So I disconnect these 2 points. This is called the normalization, and the 2 pre-images of the node look like Q1 and Q2. And this is a meromorphic differential here with 2 simple poles. The residues are automatically opposite by the residue theorem, so there is no further restriction. The dimension of this space is again 2. So it all works out. We're good? Okay. So this is my description, really. What I described for you is essentially how this space looks like in an example. Not fully, but this is some example, okay? And now I'm trying to compactify my strata, so I want to work in this space. First. So let me now say the really important thing. So what I'm saying here is all joint work, and it's joint work with Matt Bainbridge at Indiana, Dawei Chen, who is here and also at Boston College and also at Institute for Advanced Studies, Quentin Gendron, currently SEMA in Mexico, in Oaxaca, myself, and Martin Moeller in Frankfurt. So it says the following. If I take my stratum and I take its closure in the compactification of the Hodge bundle, it's the following. Okay? And I won't tell you what the following is. But it's some kind of description here, geometric, and I've given many talks about that long time ago. I got tired, so I don't want to tell you now what this is. But this, what does it say? This says this thing is a subset of a vector of a rank G vector bundle over MGN. I can compactify this vector bundle. I can take the closure of that. Technically, I should also projectivize because I don't want zeros and I want this to be compact. So maybe I should write projectivizations here, but let me ignore them for the purposes of the talk because you need to only take non-zero differentials and you need to take them up to scale because the zeros are not sensitive to this. So then this is a compact space. That's the point. And the closure is given by some conditions. Okay? And we have described the conditions, and I'll have a bit more to say about the conditions later on if we ever get there. And this is the compactification. Okay? And this is called the incidence variety compactification. It's called that because we call it that. And it's an incidence between a form and points. So this thing somehow keeps data of the points and the form in some reasonable way, and they're somehow matched up. So this is why the word incidence. So I'll call it IVC. So this is a compactification. We did it, I think, 2-3 years ago. It was published last year, but this is a couple of years old result. And there are some geometric conditions that are not, I like them very much. I'll tell you a little bit what they are, but they're nice. And this is a compactification. And I'd like to tell you that my talk is not about this compactification. And now I'd like to tell you why. So I want to try to understand what I really wanted to have meant by the word good. So now I want to write down various properties that you may want your compactification to have. So properties of a compactification. You want it to be a moduli of some geometric objects. I'm phrasing this loosely with apologies to experts on stacks, but I wanted to parameterize some kind of geometric object. So I want boundary points not to be just abstract points, but I want the boundary points to correspond to something geometric. So my space is a moduli space, right? It's a point on my stratum corresponds to some geometric data of a Riemann surface, a form, and a bunch of points. So I want points on the boundary to also to correspond to some maybe more elaborate geometric data. Okay? And if I look at the incidence variety compactification, it does have this property, meaning it does parameterize some geometric objects that I won't tell you, but it does. Okay, so that sounds good. You want it to be a reasonable compactification. So you want it to be, is the closure of the open stratum. So you see, when I compactify, I could do a silly thing. I could take a one-point compactification, say that's it, and then I can take an arbitrary variety and say this is, and take the disjoint union, and this is still a compactification. You don't really want that. So you really want that. So you really want the open stratum to be an open dense subset. That's probably what you want. Okay? So this is true. Okay? You really want it to be a projective variety, or maybe stack. If you don't know what stacks are, orbitals, never mind. This is a projective variety. Sort of automatically, it's a closure of something algebraic and something projective, so certainly it's good. Okay? You don't have to work for this, you don't have to work for this, because I've just taken a closure in a Hausdorff topological space, no issue. I have to work for this. There are some other properties, of course I'll need to look at my list now. Okay? I want it to be is the universal object for families of something. So as you know, moduli space of curves is a universal object. Whenever you have some kind of family of curve, of smooth curves at least, over some base, it comes from a pullback from the universal family over Mg. So you want to have a family of curves. You also have a family of nodal curves over Mg bar. And you want this to be a universal space. That I'm not so sure about. Okay?
What's the difference between the first property and the last one?
Some kind of universality.
So the first property just means what?
Means that there is some family of something over that. I'm being sloppy. So it's really two parts of the same thing.
Okay.
So you want there to be a universal family of something such that any family over any base, some conditions, comes as pullback. But I'm splitting this as two pieces. One, there is a family over my space, and second, it's universal in the category of something, so that everything else comes as a pullback.
So usually this universal is a little stronger. It's whatever comes as a pullback out is also unique.
Yes, of course. Yes. But I'm being
Where that's not there.
true, but that's not the real issue. So I'm trying to say, so far what I've written, the incidence variety compactifications, sounds like I have constructed something good. Okay? So you want more. You want boundary is a maybe simple normal crossing, but is a normal crossing divisor. This does not work. The compactification is smooth as a stack. And this really doesn't work. So this closure, even though it's so natural, it seems to us that it has arbitrary toric singularities. We haven't proven it, we haven't bothered. But it seems that for any toric singularity, you can find a stratum closure which contains that particular toric singularity. That's quite bad. Because what this means is there is no hope for you to do, say, intersection theory. So has good intersection theory. And of course, it can happen to have it without being smooth, but there is no guarantee. Okay? Finally, if this compactification should map to MGN bar, you want to say that your objects, your curves, are still nodal curves at worst, and that's all, and you don't blow up that. But then you're keeping track of differentials in some way. So this incidence variety compactification, IVC, is perhaps nice, but it is not smooth. It's not clear it has a reasonable boundary. It's not clear it has a reasonable universal property for something. It does parameterize something. It's a closure somewhere, and you can describe it quite clearly. The singularities seem to be quite bad. Okay?
Are you also requiring that it supports an extension of the action of SL2R? Or no?
SL2R action extends? Certainly not.
What's the verdict on the second last one?
Maps to MGN bar? Oh, yes, yes. I mean, this is a closure in the total space of bundle. Sorry. Okay. So this is maybe not as good a compactification as you'd want it to be. Suppose you are now a very good algebraic geometer, certainly much better than me. Okay? Then you would have an ideal world algebra geometric compactification. So suppose you know how to run machinery, and suppose you can construct something. So you have some fine modular space that represents some nice functor, and you say many words, and somehow maybe at the end of the day, if you're lucky, you actually can see what objects you have. Maybe not, but you have gotten yourself a compactification. So what would it then be? It would be a modular space of geometric objects. It doesn't have to be the closure of the open stratum. As you know, for modular stable maps, there are extra components of arbitrary dimensions. It's a mess. No guarantee. It would be a projective variety or a stack. It will be the universal object. The action of SL2R has no reason to extend. If you are careful, probably it will map to MGN bar. If you are lucky, it will be smooth, but that requires luck. There is no guarantee that it will be a reasonable stack if you are not doing this. It would probably have, if you are lucky, it would have intersection theory, and boundary will be a normal crossing divisor. If you were to have a nice algebra geometric compactification, this would be the properties that it has. The problem is I have no idea how to construct such a compactification. But this is sort of the checklist of properties you would want to have with luck replaced by yes. Yes?
If you are hoping to have something smooth, won't you get also, if connected, something which is the closure of the open stratum too?
Yes, sure.
Well,
Yes. If connected. Yeah. Well, I'm not saying there are no relations between this. There are. I'm just trying to say something. Okay, so here is the main theorem.
Can I ask one question about the SL2R action? So
Yes.
when you have the projectivization, that kind of already kills it, but mildly so.
Yeah.
But somehow.
Doesn't kill it. So you can. So if I take a differential and I act by an element of SL2R, I get some other differential. If I take the differential and multiply it by 3, I get the same story.
Yeah,
But if I rotate,
it, then it's a little bit different. But somehow.
maybe I should really projectivize by action of R plus, but never mind. Yeah.
Yeah, but somehow it seems like this projectivization issue and SL2R action, they're kind of related in some sense.
So if
One of the issues is exactly.
no, the issue is different. So the SL2R action and projectivization are somehow related and complicated for the open part. When you go to the boundaries, the difficulties are completely different. So suppose that when I say projectivize, I only quotient it by multiplication by positive reals. Then, of course, my space is no longer algebraic, but I have an SL2R action, well defined. But it doesn't extend to the boundary, nonetheless, because I'm forgetting some information. And there is no way to extend the action. That's not the issue. The issue is that this compactification forgets a lot of data that I would need to define an SL2R action. I'm not sure whether I answered your question. Okay. So here is the theorem. I should say it's in progress, but hopefully the progress will converge in a couple of weeks. This is with Matt Bainbridge, Dawei Chen again, Quentin Gendron, myself, and Martin Moeller. There exists a compactification. I'll call it M for lack of a better symbol to write. Maybe by tomorrow we'll decide with Dawei what it's really denoted. Of a stratum such that I'll just write a column for M and I'll tell you which properties it has. So M. Okay? So M will be a modular space of some geometric objects. It will parameterize something geometric. It will be the closure of the open stratum. It will be an algebraic variety. We don't know that it's projective, unfortunately, for technical reasons that I won't go into. I mean stack. Okay. It will be the universal object for families of suitable things. The boundary will be a normal crossing divisor. It will be smooth, and thus it will have good intersection theory. It will map to MGN bar, and the SL2R action will not extend, but extends after a real oriented blowup. Okay, so I've almost hit all the check marks, except I don't know it to be projective, I only know it to be algebraic. And I have to blow up to extend the SL2R action, which is not so surprising, because you sort of should be really projectivizing by R star anyway, and then you don't have algebraic structure and so on. Moreover, this compactification will surject onto the incidence variety compactification. So it's some kind of further refinement of that. So that's the statement. Okay, questions? Okay, so the goal for the rest of the talk is to try to give you some idea of what this compactification is.
What kind of structure does this space have?
In what sense?
I mean, it is just element per stack. Is it?
It's an algebraic orbifold and variety, finite quotient singularities. This map is locally a blow-up of the normalization of the space. It's a maybe finite branch cover, but it's only locally a blow-up, so I cannot say it's globally a blow-up, so it doesn't follow this projective.
Mm-hmm. Okay.
But that's, I don't know whether that's what you asked. Okay. So the claim is that we have this compactification, and it's really moduli space of multi-scale differentials, and I'll try to indicate to you what these multi-scale differentials are with some extra data. But before I do that, I really want to explain what's the whole difficulty in the story. Why is all this complicated? So if you didn't like any of this, you can ignore that, and I'll just try to explain some difficulty in some down-to-earth, hopefully, terms. Okay. So somehow main difficulty when taking a family, in a compactification such that the curves, so a family will be denoted X, okay, maybe X star. So this is a family over a punctured unit disk with parameter t, such that xt together with the points z1, zn, also dependent on t, converges to some nodal curve. Okay. It could happen that if I take the limit of the corresponding forms restricted to some component of x, this limit is identically 0. Let me try to explain this in an example. Okay. So I want to work with perhaps the simplest stratum of interest, omega M212. So this is the locus of Weierstrass points on hyperelliptic curves of genus 2. But let's pretend we know nothing about hyperelliptic. Let's pretend we know nothing about Weierstrass. I want to treat this as the simplest example of a general structure, right? So this thing here sits inside the total space of the Hodge bundle, which I can compactify as we discussed previously. Okay? And I can try to take the closure of this, and let's try to understand what the closure looks like for curves of this sort. So let me draw both pictures. Okay, so this is an element in the boundary of M21 bar. So this is a nodal curve with one marked point. So it's almost the same picture as I drew before, right? So the dual graph looks like that, but I somehow should label the fact that there is a marked point here. This is called point Z. So this labels that the marked point Z lives here. I have a differential omega 1 here and differential omega 2 here. And we know they're both holomorphic, so this is x1, x2. So I know that omega 2 is a holomorphic differential on an elliptic curve. Right? Suppose now I have some family in this stratum such that the underlying curves degenerate to this. What happens to the differentials? Well, the multiplicity of omega 2 at the point Z must be at least 2. Right? So suppose a point like that lies on the closure of this stratum in here. Then the multiplicity of this form at this point must still be at least 2. Suppose this omega 2 is a limit of a family of forms. Each of them vanish at the point Z, depending on T, to order at least 2. So in the limit, they still vanish to order at least 2. You can do some degree count. They must vanish to order precisely 2. But this is impossible because this is an elliptic curve, and I'm talking about a holomorphic one form on it. So I just know where 0. So this implies that my omega 2 must be identically equal to 0. Okay? And if my omega 2 is identically equal to 0, so I have no idea, I no longer have any idea where Z is, right? Because now on this elliptic curve here, I have an identically 0 form. And I'm supposed to find out which of the points on this elliptic curve, if any, was the limit of zeros of forms that vanish with multiplicity 2. And since my form now looks identically 0, I have no idea whether it's this point or that point or that point, and presumably it's not all of them. So I have lost a lot of data. Okay? And this is somehow the entire difficulty in the project. And this is a difficulty that algebraic geometers know well. So algebraic geometers working with moduli of curves since the time of Mumford, Harris, Eisenbud know that this is about limit linear series. And this particular situation, algebraic geometers could easily handle. I won't tell you how, but it can be. So if you want to think about something explicit, you can try to ask yourself a very explicit question. Which configurations of this sort, two elliptic curves with a marked point on one, arise as boundary points of this stratum within here? So meaning when is something like that a boundary point of a stratum? And the answer turns out to be that this is an elliptic curve, and it actually has two marked points, a node and this point. And the answer is that the difference of these 2 points has to be a 2 torsion point on the elliptic curve. This is the answer you can see very easily if you do hyperelliptic curves and understand where the Weierstrass points lie, but requires some work. Before you think that this is all trivial, let me give you a couple more examples of the same sort. This is still the same stratum, but slightly deeper and more complicated degenerations. So again, the issue is I'm trying to explain what the difficulty is in tracking where the zeros of differentials are under degeneration. And the issue is always the same, that the differential in the limit just vanishes on some components of the curve. Okay? So here is another nodal curve. So this is genus 0, genus 1, genus 1. Okay? So what this means geometrically is I have an elliptic curve, another elliptic curve, and they're connected to a sphere, P1, and the point Z sits on a sphere. Okay? So this is a stable curve of genus 2 with 2 nodes now. If you think about, let's call these components x1, x2, and x3, and on a sphere, again, I must have a holomorphic differential, but there are just no holomorphic differentials on the sphere whatsoever. So this means omega 3 is again identically equal to 0. Of course, on a sphere, there is no moduli, but there is a moduli of these two things. So you might wonder whether they play a role. And if you convince yourself either way, it's up to you. I won't tell you the answer. You can also think of the following situation. 1, 0, z, which corresponds to, again, I have a sphere, P1, which meets an elliptic curve and 2 points, like this. Okay? And again, I have components x1, x2, and here omega 2 must be identical to 0 because there are no holomorphic differentials on a sphere again. And now I ask you, well, this is an elliptic curve with 2 marked points. It has moduli. So does such a thing arise on the closure of the stratum? Does such a thing arise on the closure of the stratum? Looking just at P1, you won't see a difference. But of course, the whole curve is different. What happens here? So this is the difficulty. Okay? So the difficulty is to formalize that if I have a family in here, such that the curve degenerate to a fixed stable curve, it could be that the limit is identically 0 on some component. Okay? So here is how you deal with this family, or with this problem. Here is a proposition in the algebraic category. So suppose x, z, z1, zn, capital omega. This is a family over a disk which sits inside an open stratum. Okay, so this is a punctured unit disk. Is such that the limit, this setup, as t goes to 0, of xt, z1, zn, is some stable nodal curve. Then, for any irreducible component, for any component of this thing, xv of the nodal curve, there exists a unique integer such that there exists a limit as t goes to 0 of omega t restricted to xv, but not just the limit, but you have to multiply. Sorry, didn't write it nicely. And this limit is not identical to 0. Okay? So I want to say that for every component of the curve, the limit may not exist, or it may be identical to 0, but it has either a pole order or a 0 order. And I can just twist out, divide, multiply, whatever the right word is, by the corresponding 0 pole order. And it's all algebraic, so this vanishing order is an integer, positive or negative. And if I try to multiply by another t, the limit will become identical to 0. If I divide by t, the limit will be infinite. Okay? I like to denote this limit to be called eta v, and this will be called scaled limit. Okay? And this is scaled limit in a family on a specific component. Definition. A multi-scale differential on X, which is the union of its component, is just a collection of such together with one more piece of data that I'll describe in the remaining in a couple of minutes, was the data of a prong matching. Okay? We'll worry about prong matching in a second, or in 2 minutes rather. I want to try to understand what kind of an object this eta is. So eta V is nothing but a meromorphic differential on the individual component, right? Where will its poles be? Well, certainly at the nodes there can be poles. There can be no other poles. Whose zeros are only at some zi, at those zi's that lie on the component xv, and some nodes, and whose poles are only at some nodes. Okay. So it's a meromorphic differential so that it has zeros where it should have zeros of correct multiplicities, but it might have extra zeros and poles at the nodes. And there are many conditions that it must satisfy. If you look at the definition, there is some kind of match in order condition at each node, match in residue condition, opposite residue condition, at simple poles, some kind of ordering condition which I won't tell you about. It somehow says that you know which components are larger and smaller. And there is some kind of global residue condition. So these are actually all the conditions that characterize the incidence variety compactification. I won't tell you what they are, but the paper is out. You can enjoy reading them, or you can not enjoy. It's up to you. But this is roughly what it looks like. Let me return to this example, which is here for a reason. So I wanted to tell you in this example what eta 1 and eta 2 will be. So you see in this example, if I just take the limit, omega 2 was 0 identically. So it means I should divide it by some power of t. So if this is a point z, this is a point q, q1 on one side, q2 on the other side. And eta 2 will be a meromorphic differential in this component, which will have a double pole here and a double zero at z. Okay? And eta 1 will be omega 1, which will be holomorphic. Okay? So in this particular example, if you have such a family degenerate into such a, if you have a family of differentials in this stratum, degenerate into this stable curve with this marked point, the limit must be identically 0 here. So the scaled limit will be something else. I'll rescale it. And I'm basically rescaling by some power of t. So the limit is no longer identically 0. And the resultant thing will have a double 0 here. So the total degree is 0, so it must have a double pole here. This is the only points where the scaled limit might have zeros and poles on this component. This is what it is. Notice that the canonical bundle here is 0, right? I mean, it's an elliptic curve. So for this to have sections is equivalent for this to be 0, which is exactly to say that 2q2 is equal to 2z, which is to say that points q2 and z differ by a 2 torsion point on an elliptic curve. That's the condition. And there is no condition here. So we have what I've told you is the intersection of the closure of the stratum with this locus and the Dilley-Mumford compactification is precisely the locus where the difference of these 2 points is a 2 torsion point, and there is no further condition. I haven't proven it, but that's the correct statement. So this is an example of what the scaled limit is. Okay? And what is M? M is a moduli space stack of multi-scale differentials. Okay, so this is the moduli space. So the compactification is the moduli of such collections together with the data of a prong matching. Okay, so I have 4.5 minutes to indicate something about prong matching, which is essential, otherwise everything breaks down. But any questions before that?
So in this case, the IVC and this multi-scale differential just agree in terms of the data.
In this case, for this particular stratum and M21 bar, they're the same.
Yeah.
I can tell you precisely, but I wasn't planning to do it in the talk, what happens. So you blow something up. So there is some kind of dimension jump over some strata. Not over the stratum. Over the stratum, nothing happens. I mean, the prong matching is also trivial here, but that's... So basically, the simplest example where something happens is for this dual graph. So for this dual graph, where this is on the same level, so the power of t is the same here and here, the m keeps track of the scales of these two things individually, the IVC forgets the scales. So there is a one-dimensional fiber of the map from m to IVC over this stratum. But that will be for the second hour of the talk.
So this limit, the limit that exists that you're about to erase, I mean, you're scaling some differential forms in some vector spaces. So what? I just don't understand, what does that limit mean? You're multiplying it by a number which doesn't have anything to do with the coordinates on the space.
Yes, but so I have a family of Riemann surfaces, of smooth ones, right, which degenerate to a nodal one. And on each of these guys I have a form. And then I want to take the limit of these forms as I go this way, and this is parameter t along the base. And if I just take the limit might be identically 0 on this component, on this one component of the nodal curve.
But if you multiply on the whole curve by a huge number.
Yes. So this limit will not exist on this component. So think of it differently. So here is my family, right? So here is my total space X, the total space of the family X. And over that space I have the total relative one form omega. It has a 0 locus in the total space, which will be of codimension 1. It will consist of two kinds of things. There will be the marked points zi, which sort of give sections over the base. But it will also contain the 0 locus of omega global. It will contain some components of the singular fiber, which are the ones I twist out. Okay? So this limit, I mean, this, if I take this L, and I've gotten a non-zero limit on this component, I will certainly get identically infinity on that component. Make some sense?
Is negative usually, or
Say it again?
is negative?
Depends on how I do my family. So it could be that if I am careless, my limits are infinite. Right? So if you somehow scale it in such a way that the total area is 1 or something like that, then else will be negative. Yeah. So I wanted to tell you a little bit about the issue of prong matching. Okay? Well, now we have 1 minute. Okay? But I know that the t is only at 3:30, so it's okay. So prong matching is, and this also gives you a hint where, how the proof actually goes. So this is somehow in a plumbing construction. So suppose I have two small disks with coordinates u and v. And suppose here I have a form which has the form u to the k du over u. And here I have the form, some constant, v to the minus k dv over v. Okay? And I want to identify them. So the plumbing cuts out such things, identifies the boundaries somehow. So I want to glue by the map uv is equal to some t. Okay? And I better hope that my two forms match up once I've done this gluing so that they extend to a global form. If I do that, so this is omega 1 maybe, this is omega 2. So what I want is I want to say that omega 1 of t over v is equal to omega 2 of v. That's what I want to have. Plug it in. What you'll get, maybe I'll mess up, but what you're getting is t to the k is c. Okay. So this means if I start with the knowledge of these two forms on the two sides, I have only finitely many choices of how I glue them. The choices differ by a different choice of a root of C. But there is no way to distinguish these choices. If I have a nodal curve, I can choose any root and start deforming in that direction. So starting from a nodal curve, I can deform in k different directions. This is the data of a prong mesh, and it's called prong meshing because in terms of flat surfaces, it identifies horizontal directions on two sides. So this is the data of a prong meshing. So it's a finite amount of extra data. Okay? When I said multi-scale differential, I was sloppy as to how exactly I projectivize them. So I really projectivize them level by level, which is crucial. I didn't say what the levels are, but these are the values of L, these parameters. Okay, so this is roughly the compactification. We don't know how to construct it algebraically. I wish we could. So what we do is we somehow follow the augmented Teichmuller space route. So we take a suitable, hugely enlarged Teichmuller space. We consider some bordification of it, which is not compact, such as the action of the mapping class group extends, and then we argue that the quotient is an algebraic stack. And that's what we do. Which is why, the functoriality and all this, it would come from a properly geometric construction, does not come for free. But that's what we can do. Okay, thank you.
Questions?
Okay.
By the way, I don't know exactly in the details how you define this modular space, but from the way you described it, doesn't it come in some sense naturally as an iterated blow-up of the incidence variety compactification?
Yes.
So
locally, only locally. Yes, so we have a very precise description of what ideal you need to locally blow up on the instance variety compactification to get this thing. It's not iterated, it just blow up.
As a blow-up, don't you get then its projectivity?
Excellent. So you take the book of Hartshorne, you'll go to the last page, and there is an example of Hironaka, which gives you a cubic threefold and another projective one. And then there is some kind of ideal that you blow up that's defined only locally. And the blow-up is not projective. And we cannot avoid that situation. I think Greg was next.
What about quadratic differential?
We haven't done it. So the status is, I pretended these were all holomorphic one differentials, right? The IVC paper, the instance variety compactification, we could do for meromorphic. And then we had a separate paper where we did k differentials for arbitrary k. There are some combinatorial issues which are very messy, but sort of as you'd expect, you go to some cover, something works out, you argue what you need to argue, and then it works. This is what we did for k differentials in that paper. What we actually do in the paper, which is supposed to be finished in a couple of weeks, is we construct this M for meromorphic one forms. There is no doubt in any of our minds that it works just as well for meromorphic k differentials together with this combinatorial issues.
You had the checklist.
Yeah, the same. It would be the same. It's the same. The properties would be the same. But the technical issues are annoying. And this paper is currently 110 pages, and all of us are more than sick and tired of it. So I don't think any of us will do multi-scale k differentials. Maybe if somebody at some point comes up with a much better algebraic construction of this moduli space, maybe then somehow k differentials would be cheaper. Richard?
No, I was just wondering about the projectivity question again. I mean, you do know that compactification is normal divisor, normal crossing divisors, right?
Yes.
So can't you just pull back the ample bundle and then twist by?
It's only whatever normal device is only local conditions. I don't have anything global, right? So basically, the issue with this Hironaka counterexample that you can have a local blow-up which is not globally projective is when locally this thing looks like a divisor, but then you go around and it comes back and maybe it's a different component it's a different locally reducible component of the same divisor. It doesn't work so well. We tried hard. So there is no cheap way to do it. Because, if you know a cheap way to do it, that would be great, but the first 5 attempts anybody of us made would also prove that Hironaka counterexample is projective, and that's not such a good idea. We can't really, if I were to bet, I'm willing to bet that our thing is projective, because it's tantalizingly close to that, but we don't have a proof.
In the case related to the question of K differentials, isn't it hard to get smoothness, since at the boundary you have components which are bigger, right? The ones which are K powers of differentials.
Yeah, so that's an issue. So then you need to take out those components, and then you don't compactify the entire stratum. You just take the stratum which are not K powers of differentials.
So you get some extra conditions at the boundary.
Yeah, you basically need to know. So what happens for K differentials? There is for holomorphic K differentials, the component that has K powers of holomorphic one difference has dimension 1 higher than everything else should be thrown out.
Other questions?
All right, if not, let's thank the speaker.